Greetings, everybody, and thank you so much for joining us today. We have quite a big crowd in attendance today, and we are so glad that you could join us. Today, we're going to be discussing, today it's going to be Antennas 101. We're going to be talking about choosing the right antenna for the job. My name is Cheryl Jennison DeProsa, and I'm joined by Fernando, and Fernando's going to be taking us through this training. But before we get into it, I just wanted to make a few notes of housekeeping. First of all, due to current circumstances, we are not recording from our usual controlled environment. We are broadcasting from our homes. So if there are any audio or bandwidth issues, please bear with us. We're just trying to make sure we get this information out to you despite our current circumstances. So please be patient, but I think we should be good to go today. As we go through this webinar today, if you have any questions, please feel free to type those into the question pane. If you don't see the question pane and you're on the web app, you should see a little circle with a question mark on it. If you click on that, that'll give you access to the question section. If you're working from the GoToWebinar Control Center, you should see a gray toolbar with an orange box with a white arrow on it. And if you click on that, that should maximize the pane and give you access to questions. Type in as many questions as you have. We're here to answer them, and we will get to as many of those at the end of the session as we can. Last of all, this webinar is being recorded and will be available for on-demand viewing. It'll take us a couple of business days to get it edited, so please be patient. But once it's ready, it will be uploaded at shure.com/webinar. I'm going to repeat that, shure.com/webinar. I also want to point out that there's a lot of past webinars across a lot of different topics. So please feel free to go there and review all of those on-demand webinars. There's a lot of great learning across a lot of great audio topics. So that's shure.com/webinar. In addition to that, if you're not aware, the Shure Audio Institute has a lot of additional online courses and certification programs, and you can go to shure.com/training to catch all of those free learning opportunities. So that's shure.com/training. All right, I think that wraps up all the housekeeping. We've got a lot of information today, so we might as well dive right in. So please, take it away, Fernando.
Yes, absolutely. Hello, everybody. It's a pleasure to be here and to be able to talk to you guys today. I hope you enjoy the information that we're going to share here today. And of course, that, as Cheryl mentioned, keep the questions and do the questions, please, at the end. So we're going to be more than happy to help everybody with the doubts and questions and etc. So let's start from the beginning. So when we talk about antennas, I think it's very, very important to understand how does antenna work. So first of all, why does antennas are so important for RF systems? So that's because any wireless microphone or wireless in-ear monitor system needs antennas to both to transmit and to receive the audio signal and all the other content that is transmitted wirelessly. So antenna is a very base element of any and all wireless systems. And basically, what is antenna? Antenna is a conductor. It's or an array or a group of conductors that translates or transmits and receives electromagnetic waves. That's the base of an antenna. So to understand that, let's just do a little introduction of what is electromagnetic wave. Actually, an electromagnetic wave, it's a composite of two fields, an electrical field and a magnetic field. Both fields together makes an electromagnetic wave or electromagnetic field. So one cannot live without the other. So every time that you have electric wave or a electric field, we're going to have a magnetic field. So what does create that kind of wave? It's necessary electrical current in a conductor, of course, to generate that kind of wave, that kind of electromagnetic wave. And everybody knows that electromagnetic waves travels in a vacuum. So we don't need a medium. We don't need a material or something. We just need and nothing. That is the vacuum actually. So the absence of any material. So that's the first very big difference between a sound wave, for instance, and an electromagnetic wave. A sound wave needs a medium to travel, no, but the electromagnetic wave doesn't need a medium to do that. So other interesting fact about electromagnetic waves that is that they travel long distances. um, and then, with that in mind, I usually in my trainings and in my webinars, I use that kind of image to understand better how does electromagnetic waves travels in the space, in the air or in the materials. Um, so what is that image? It's the effect that happens when you drop a rock in a lake, for instance. So everybody knows, even from our childhood, etc., that when you do that, you create waves that travels in the surface of the lake. So if you imagine that the radio wave or the electromagnetic wave uh, has some similarities with that phenomenon of dropping a rock in the lake, you can understand how the waves travels, how they spreads. If you think that you have an energy that comes in a certain point of space, and with that energy, this energy is spread in a way of a wave in all the directions. And if there is a wave, there is a propagation velocity. So because the wave we're going to travel in space. So if you're going to travel, you're going to have velocity related to that displacement in the space. And of course, that as far as we go from the antenna, the weakest we're gonna be the energy that we're gonna sense. So now, for instance, in this little animation, you can see that the red dot represents how the energy is generated and how it propagates in the space, and how in a point that is the green point, it's the receiver, senses that energy that were generated at the antenna. So let's talk here a little bit about the antennas. You can imagine here that you have a transmit antenna that is symbolized here by the TX letter, and the receiver antenna is the RX that is separated in space from the transmitter antenna. So with that in mind, we can do what we call the electromagnetic wave equation. What is that? Well, if the waves is transmitted in space with a velocity, we can calculate what we call the wavelength. What is the wavelength? The wavelength is the space that is that we occupy when we have exactly one space, one frequency space, sorry. So if we consider the velocity of the wave, and if we know the time, we can calculate the wavelength. Or if we have the velocity and the frequency of the wave, we can calculate the wavelength. How does it works in electromagnetic wave? We need to know what is the velocity of the wave, of the electromagnetic wave. So approximately the electromagnetic wave has the same velocity of the light. So the light travels around 300,000 kilometers per second. Oh, it's close to 186,000 miles per second. So with that in mind, we can calculate the wavelength very easily. We only need to know the frequency. No? Just a curiosity, the distance between the Earth and the Moon, it's approximately 384,000, 384,000 kilometers. So it's approximately 1 second and something from the Earth. So if we transmit a signal from the Earth, it's gonna arrive at the Moon like 1 second and something. Just to have some more idea, how fast is this velocity? So 300,000 kilometers per second. It's really damn fast. It's actually is the fastest velocity that we have, and then we know. So that's very interesting to understand that sometimes people asks me, for instance, how long does it take for a microphone signal to travel from the transmitter to the receiver? So it's really damn fast because of that velocity. So it's almost instantaneously. So because of that, if we calculate the wavelength, we can do a little trick, a mathematical trick here. That is, if we put the velocity in meters, it's going to be 300 million meters. So if we think that we're going to do the calculation with the frequency in megahertz, we can cut the zeros, and the formula here is going to be very easy. So doing here in this kind of calculation, we can do like the wavelength, it's 300 divided by the frequency. So with that calculation, we're going to have the wavelength in meters, of course. So for instance, if we took like 600 megahertz, that is one of very common frequencies that we use in our wireless systems and in ear monitor systems and etc. So if we calculate the wavelength here, it's going to be a very difficult math. It's 300 divided by 600. So it's half a meter or 15 centimeters. To have that calculation, do I need to do that calculation every day? I'm an audio engineer. Do I need to do that? Do I need to understand that? Of course, that you will not gonna do that calculation every day, but it's very important to understand the importance of knowing about that wavelength. So if we took a microphone and this microphone is transmitting a signal of 600 megahertz, you can imagine that you can see in the space the wave as it's going to be like 50 centimeters long or half meter long. So that's very important, because we're gonna, as we know about the relationship about wavelength and the objects, we're gonna understand how the objects will interfere in the travel of this wave, for instance. If we do calculate and the wavelength for 2.4 gigahertz, we're going to see that the wavelength is going to be shorter because the frequency is higher. Actually, the frequency is 4 times higher than 600 megahertz. So now the wavelength is going to be 1/4. So you know that when you look at your Wi-Fi router or the antenna that you use for Wi-Fi systems, you're going to see the antennas, they are shorter, for instance, than our antennas used in UHF microphone systems. So that's why. So there is a relationship between the wavelength of the frequency that we are using and the antenna size. That's why it's so important to understand this relationship, this very basic and simple relationship. The wavelength has a connection with the length of the antennas. The same way, of course, if we talk about audio, we can think about that the wavelength of the audio signal, for instance, the acoustic signal, has some relationship with the size of the speakers. So it's the same idea. Of course, that we are talking about different things here. One is electromagnetic waves, the other is sound waves, but you can relate and understand better. Wow, now I understand that the size of the antenna has some connection, have some relationship with the frequency that I'm using and with the size of the antenna. Uh, so just for us to understand, if we took a signal of 2 kilohertz and we calculate the wavelength of that electromagnetic signal of 2 kilohertz, we're going to see that the wavelength is really, really big. It's like 150 kilometers. So there is no way to do a effective and efficient, antenna to work with 2 kilohertz, because the antenna is going to be very, very big. So now from that information, we can relate better the size of the antennas and the frequency that we are using. Another point to understand the antennas, or how does antenna work, is to go back with a basic electric circuit like this one, that we have the battery on one side and a lamp in the other side, and the two conductors making the circuit and making the electrons flow and make the lamp blow light. Sorry. To understand that phenomenon and how an electric circuit like that works, we're gonna make us easier to understand how antenna work. So how can a conductor, how they can turn in an antenna? When I started working with audio or something like that, it always keeps in my mind that question. So what is the difference between a conductor and an antenna? If antenna is a conductor, where is the separation between them? How does this physical phenomenon happens? So it's very complicated to understand if we took the formulas and all the math behind it. But if we try to understand in a more practical way, it's very interesting to understand that. So in my example here, I'm going to take a source that I called a RF energy source. That is something that we're going to generate RF energy. Can be all the power circuitry of your transmitter, all the electronic circuitry that is inside your handheld microphone, or inside your in-ear monitor transmitter. So it's a source of RF energy, electromagnetic energy. So if we want to transmit that, we're going to have a conductor or two conductors to be able to transfer all this energy from the source to the receiver or to the load. So we can think about that as a way to transmit from the in-ear transmitter to your body pack, or can be even from the output circuitry of your microphone to the antenna. So it may be, we should have a way to transfer that energy. So that energy, it's electrical energy. So it's gonna be like an electrical current flowing in these two conductors. So there's a energy flow from the left side to the right side. So that's what happens. We can easily understand that. Okay, there's a source and there's a receiver. Okay, energy is flowing. Good. But how can I turn that in an antenna? How can I turn that in a way to transfer the energy to the air? So because I'm not gonna use the conductors. I'm gonna use the air. I'm gonna use the no conductor to transfer that energy. So the magic here happens when we bend the ends of these two conductors in a way that it makes two little conductors spaced in the air in this configuration. We call that a dipole. It's two poles, one on the top, one in the bottom. So we have two poles that magically the energy will keep flowing from the left to the right, but you can see here that the current, we're going to be in the same direction. That makes the magic. That makes the electromagnetic wave to travel in the air as a radiating wave. And that's what we call a kind of half wave antenna. That is made just simply by separating two conductors in the air in that configuration that you can see here in the picture. So our antennas, our cables, and our accessories that we're gonna mention here today, used by microphones and in-ear monitor systems. Sorry, all of them are 50 ohms. What makes that 50 ohms? This is a characteristic of the antenna, or how it transfers the energy from the conductor to the air. So it's not easy to measure. You cannot measure the impedance that is 50 ohms using multi-tester or a ohmmeter. We do need a special equipment to be able to measure that impedance. But I'm just put it here as a side note. So everything that we're going to talk from here, it's based on antennas that is 50 ohms of impedance. Understanding how an antenna works, now it's very interesting to understand what is the polarization of an antenna. If you took what I put it here, you can see that antennas, the two elements, the two dipoles, are in the vertical orientation. What does I mean by vertical or horizontal? Every time that we talk about vertical and horizontal, we are saying related to the Earth, because we are from now living in the Earth. So Earth is our reference. So if we say that we are vertical, it's related to the Earth. And if we say that we are horizontal, sorry, we are related to the Earth. So these two dipoles that we can see here, they are vertical oriented. That's important, because if we have a transmitter antenna that you can see here in the picture on the animation on the left, and you see a receiver antenna here on the right, we need to imagine that the better transmission we're gonna happen if both antennas are oriented in the same way. So in this application, if I do need to transfer the energy from the transmitter to the receiver, is what I normally want to do in a very effective and efficient way. We do need to put both antennas in the same orientation. When we call orientation, we are saying about polarization. It's not polarity. We can confuse that. Polarity is related with charge, and here polarization is related to the position related to the Earth. So both antenna here that you can see in my animation, both antennas are vertical polarized, like we call that, with the polarization. If we took like the right antenna, the RX antenna, if we put in a different polarization, it will not gonna receive the same amount of energy. We call that, we're gonna reduce the efficiency of the transmission. So this is one of the very important things to understand related to antennas. If we want to keep the polarization, we were gonna increase or we're going to keep the better energy transmission from TX to RX. Okay. So I think that we all that introduction, you now understand better how antenna works and what is the phenomenon, the physical phenomenons related with the antennas that we're going to use in the entertainment industry, like for microphones and in-ear monitors. So let's talk a little bit, as this webinar is related to antennas 101, let's talk a little bit about the basic antenna types. So the first antenna that normally all the books shows and explains is what we call a theoretical antenna. Why is theoretical? Because it doesn't exist. We cannot do that physically, because an isotropic antenna is an antenna that radiates the same energy in all directions. So it's not possible or doable, as far as I know, to do that in a practical way. But why does this antenna is so important? Because when the engineers and all the people that started studying antennas, they put that to use as a comparison. So all the other antennas, we're going to be compared with this one. So we state that the gain of isotropic antenna, it's the ideal 0 dB. So that's why we call a 0 dB I antenna, or again of 0 dBi, because dBi relates to an isotropic antenna. An isotropic antenna has exactly 0 dB I of gain in all directions. That's why. So if we took, for instance, the first half wave or the most used half wave antenna, it's a dipole antenna that we see in most of the wireless equipment that we use in audio. So if we took a look at that antenna that is pictured here, you can imagine that it is made of two separate parts. One is 1/4 wavelength, and the other is 1/4 wavelength. What makes, sorry, there is one, sorry, that's what makes a half wave antenna. That's why a dipole, it's called a half wave antenna, because it's made of 2/4 waves elements, 2/4 waves dipoles that together makes a half wave antenna. What is the pattern of dispersion or radiation of this antenna? Of course, that it's not more omnidirectional in all directions as the isotropic antenna, because it's a theoretical antenna. Now it's gonna be like a real life antenna. So it has that pattern that we call a donut or a toroid, or okay, but we call that normally omni. That's because it's omnidirection in the perpendicular direction of the antenna. So if the antenna here, it's vertical polarized, as you can see, the wave, we're going to travel horizontally, and the maximum gain of this antenna is in the horizontal plane. So as you can see here, symbolized by this donut, that's exactly how does the energy spreads from the antenna. Or It's the sensibility of reception if this antenna is a reception antenna, a receiving antenna. So understands that this pattern will gonna work in even if the antenna is for transmitting or for receiving. So it's the same pattern of transmitting and receiving. Of course, that we cannot use, or we normally don't use the same antenna for both transmit and receive. Of course, we only use normally antenna for only transmit and only receive. So that's very important to understand. Uh, in this little table here on the right, you can see that this antenna for audio use, we're going to have the impedance of 50 ohms. The gain of the antenna now it's measured against the antenna, the isotropic antenna. So this antenna, for instance, it has 2.15 dBi of gain. What does this mean? It means that this antenna has more direction than the isotropic antenna. If you imagine that, if I took the isotrope figure that you saw in the past slide, if we press the poles of this ball, if we squeeze it a little bit, it we're gonna put the energy more in the horizontal plane. So that's what happens here. Why does this antenna, the dipole antenna, has more gain than the isotropic antenna? Because it has more energy in one direction than the other. So one very curious fact here to understand is that when you increase the gain of the antenna, you're going to increase the direction, or the, how can I say that in English? Sorry. We're going to put more energy in one direction. So if we took antenna, for instance, of 14 dBi, you're going to be more directional. You're going to put more energy in one direction. That's the meaning of the gain here for the antenna. So when you increase the gain, you are putting more energy in one direction. So you are doing an antenna that is more efficient in one direction than the other direction, for instance. So this dipole antenna, it is more efficient in the horizontal plane, in the horizontal travel of the wave, of course. But in the vertical, you see that the donut doesn't have any energy, or almost nothing. So that's explain why we should keep the polarization of the antenna. That's why the polarization is so important, because if we rotate one of the antennas, we're gonna decrease theoretically the transmission efficiency. And for a dipole antenna, we can say that it has like a beamwidth, like how the energy spreads. It's 360. And the pattern is the donut, as I said before. And the polarization here that you can see is vertical. Of course, that if we put the antenna on a horizontal, of course, the polarization is going to be horizontal. If we put the antenna on the vertical, the polarization is going to be vertical. So it's very smart to take a look at the antenna conductor, and the antenna conductor direction will explain how the polarization is. So that's the trick. We can normally see that kind of antenna in every professional wireless system. Both you can see that normally in transmitters or in receivers also, and body packs. You can see here in a QLXD system, that's very normal. So why, Fernando, this antenna on the QLX system, it's not vertical, it's not horizontal, it's like in the halfway between both. That's the one very good and clever idea, to keep the antennas apart from one another, and of course to keep it the same activity of reception, independent where are you holding the transmitter, if the transmitter is exactly in the horizontal orientation or vertical orientation, for instance. The antenna below here, it's one UA 860. There is very common antenna, very good antenna also, but it's a dipole half-wave antenna. And the conductor here, it's with a polarization in the vertical, so this antenna is a vertical polarized. That's one. That's everything about the dipole antenna and its importance. The second antenna, it's what we call a monopole antenna. So what is the difference between dipole and monopole? Well, dipole, we do need two poles. We do need two elements in the antenna. The monopole, we do need just one element. So what happens here? It's like a dipole cut it in a half. It's like the half size dipole. So the element, the transmitting element, it's just 1/4 wavelength. So that kind of antenna do need a ground plane to work. What is a ground plane? Well, it's like the second half of that dipole, but the dipole doesn't exist, and you using actually the ground or the chassis of the equipment as the ground plane. So this antenna, it's like a phantom dipole. The second dipole, the second pole, sorry, to make a dipole, it's below the ground. So it's like a phantom, as you can see here. So what is the diagram of radiation? No, it's almost the same, but as the dipole, but cut it in a half. So it's what we call normally the half donut or the half dipole. Of course, it is still a omni antenna. The polarization is the same. You see the bandwidth and the impedance, and in the gain is a little bit higher. Why does this happen? Is the effect of having the ground plane? It's gonna double the energy that it spreads. So this in this example that you can see here in the picture, you see a BLX system with a monopole, a quarter wave antenna. And that's how it works. Let's get a little bit complicated now. So the next antenna, it's the very famous, the most used, I think, or the most seen in big shows and events, is the LPDA antenna. LPDA stands for log periodic dipole antenna. Log periodic dipole antenna. So dipole antenna, it's antenna with two poles. So actually, LPDA, it's an array of dipole antennas. Yes, it is. It is. So actually, this antenna is made of like 4, 5, 6, 10, 15, 12 dipoles of different sizes. So if it has different sizes, it's going to work with a broader frequency range. So it's like having, for instance, different dipoles for different wavelengths. So different frequencies, frequency ranges. So it's like putting together like 10 dipoles or 4 dipoles or 8 dipoles, and etc. So it what I call normally in the trainings like a line array of dipoles. What a line array does in a speaker system, it makes more directional. So that's the idea behind this antenna. This antenna is more directional than the dipole. It's gonna do that group of antennas. We're gonna work together in a way to change how the antenna works. This is one thing that we need to understand. if any conductor can be an antenna, if a conductor is an antenna or can be an antenna, if I put more conductors together, I'm gonna have a different antenna. So that explains what I'm going to show in the later in the next slides. I'm going to show that we can't put the antenna close to like steel surfaces or conductor surfaces because we're going to change the pattern of the antenna. We're going to change how the antenna works, and we don't want that. We don't want that. We don't want an antenna that does its job. So we can't have anything that's different what we think or what we want. So these antennas are arrays of antennas, the LPDAs, that they were designed for that. They were designed for being directional. So normally these antennas are more directional than the dipoles. Like for instance, these ones that I'm showing here, the PA 805 and the UA 874, both are LPDAs that you can see a lot of equipments over there. So the antenna on the top is a passive antenna. What does it mean? It means that it doesn't have any electronic inside. It only has the conductors or the elements and the wire and etc. and the connector. It doesn't have any electronic. So if an antenna is passive, it can work for both transmitting, and also you can use that for receiving. You cannot use for both at the same time, for receiving and transmitting, but you can use the PA 805 for a wireless microphone. You can use the PA 805 for a in-ear monitor system. So that's very interesting because you have antenna that can do both ways. You can use today in a microphone and tomorrow in a in-ear monitor system. So, but that you cannot do with the active antenna. So the antenna below, it's an active antenna that is a LPDA antenna with an amplifier. It has an amplifier, and this amplifier has their electronics inside that amplifies the signal, the RF signal the antenna captures or the antenna receives. So this amplifier, it has a direction. So you can only use this antenna that is shown here. You can only use for microphones because it is a receiving antenna with amplification. You cannot use this antenna, for instance, for in-ear monitors because you need to transmit. So the antenna on the top, the PA 805, you can use that for monitors because it doesn't have any electronic. In an antenna sense of way, both antennas are the same, are LPDAs with almost the same frequency range, etc., etc. So this antenna, it's like 6.5 dBi of gain because it has more, it's more directional than the monopole and the dipole, for instance. So that's what 6.5 dBi means. And different from the monopole and the dipole, the rear rejection of this antenna is 15 dB. So if you see on the top, like the cardioid like pattern of transmitting and receiving, you can see that in the back of the antenna it has some rejection. So the other use of this antenna is to reject the energy that is coming from the back. So as it is directional, we're gonna attenuate the RF energy that is coming from the back. So that's what we call rear rejection. So the numbers here, just to make clear, it's a number that is approximately that. So 15 dB is approximately that. It can be a little bit less or higher depending on the frequency and depending on the type of antenna and the frequency range and etc. So that's only some ideas to you understand the biggest difference between an omnidirectional antenna that has no rear rejection and like the LPDA that is a directional antenna that has some here rejection itself. So that's an LPDA antenna, very used. You can see a lot of places in a lot of shows. A second directional antenna here, very common also, a helical antenna, HA8089. What happened here? What happens here? Sorry, it's very funny. It's an antenna that is actually it's a monopole. Uh-huh. Yeah, it has this plate on the back. You can see here like this, like a dish that is a conductor that works like a mirror and an isolator also for RF. And it has this element here in the center that it's a monopole, but it's a circular, like a helical helix conductor. So a different fact happens here. The polarization of this antenna is not vertical, it's not horizontal. Actually, it's both in its all directions. So it's what we call a circular polarization. So it doesn't have a specific polarization. It has just a circular polarization. Why? Because if we use that antenna, for instance, for receiving, this antenna will show the same sensitivity or reception if we put a transmitter in any polarization. So it's going to receive the same energy independent if the transmitter is horizontal polarized or vertical polarized. So that's what we call a circular polarization antenna. It's more directional. Like, for instance, this one is 63 degrees of bandwidth. Its gain is higher. It's like 10 or 12 dBi. So it has a very higher gain. It's more directional. And I hope that from the beginning until now, you can understand better what is the difference and what is the application of all the antennas. So we have some omni antennas, we have some directional antennas. As we go, as we increase the directionality of the antenna, the gain increases. Normally, the here rejection increases also, and the beamwidth, decreases, get more directional. Other antenna there is helical also. It's the domed helical antenna. It's very similar to the last one that we showed, but here we have the dome, we have a different design. It's circular, polarized also. It's directional. It has a beamwidth of 72 degrees. It has a huge, like we call that, like a good here rejection. It's a very good gain also, 9 to 11. So it's almost the same, let's call that. They are different antennas, but of course they are similar in some technical details here, of course. And of course, that another antenna that we're gonna be the last one antenna that I'm gonna show here today. It's like we call the low profile antenna. It's a different kind of antenna. It's designed with some flat and plain elements in a circuit board, and it's a very low profile, so it's very easy to put in your like in your office, inside the theater, in the ceiling or in the wall, in the any kind of corporate room, because you can even paint this plastic cover and so on. So it's a different kind of antenna. It's directional. The bandwidth is close to 100 degrees. It has, again, close to the dipole. It's 2.5 dBi. And the polarization actually depends on the installation orientation. So take a look at the manual to understand that. But it's a different kind and different type of antenna. This is the last antenna that we're going to show here today. Of course, that there is like more 100 or more than that kind of different antennas. I suggest you to take a look at your streets. Not nowadays, not really, but we're gonna take a look at the poles that you see and the telecommunication towers. We're gonna see different kind of antennas. And there's a lot of different designs, like Yagi, like a microstrip, and whatever. So there's a lot of different type of antennas over there for different services and different areas. In the entertainment industry nowadays, these antennas that I show you guys is the most common antennas that you can see in the field. So that's why I keep that in my presentation. But if you are interested, take a look, do Google some research. If you have time to find some books on antennas, it's very interesting area. As much as you understood about antenna, more we're going to take advantage of them. So I'm going to show here just 2 or 3 different type of antennas. That's not the 2 regular antennas, just to let you know, guys. This one VHF antenna. So as it is VHF, it works in a lower frequency range. So if you remember about the wavelength calculation, if you lower the frequency, the antenna is going to be bigger. So this is a kind of antenna that, because it's bigger, because the wavelength is lower also, we do need this plate that you can see here in the picture. That is the ground plane. So it's a different kind of antenna. It's made for the VHF frequency range, but of course you can use that in VHF systems. Also for a VHF system, we have also an LPDA for VHF systems. This is the UA874V. So you can see here the technical details on the right. Of course, it's LPDA, it's the directional, but it's made exclusively for the VHF frequency range. And also, we have also a 2.4 gigahertz antenna that is made for the dual XD, or even you can use that in the ShowLink system that we have in your Accent Digital system. And so it's a directional 2.4 gigahertz antenna. You can see by the picture that it's a very small antenna. You can see here by the tripod adapter, you can see that is a very, very small antenna. Why? Because we are using a higher frequency range, so the antenna is smaller. It's related with the wavelength, of course. Now, for the end of this webinar, I'm going to show some antenna position, some suggestions. Of course, there is no rule, but there is some suggestions. Sorry. So the first thing that you need to understand is related to the frequency range. So antennas, cables, receivers, amplifiers, distributors, combiners, they must be for the frequency range that we're going to use in your system. So take a very care of looking at that. The other point of antenna placement, basic, it's to keep separation between them. As you understand now, any conductor or any other antenna can change the pattern, the reception, the gain, the impedance, if we put 2 antennas too close together. So what is the rule of thumb here? Mount the antennas at least 1 wavelength apart. So keep them separate. This is an idea. This is the, if you do the calculation, you're going to see that with distances greater than 1 wavelength, they were going to start to separate, and they're not going to interfere with each other. So keep them apart. So if you think about one wavelength of 600 megahertz, it's half meter. So what we usually say is keep like half meter apart, 1 meter apart, 2 meter apart. So as you put them far apart, there will going to be less interaction. If you put them closer apart, we're going to be more interaction. So keep them away. Keep the antenna away also from any metal objects. Antenna is made of conductors. You saw that. You saw that a dipole, a LPDA, it's an array of dipoles. So if it has more conductors, you should keep them away from other conductors. So keep antennas away from metal objects. Can I put the antenna inside a plastic bag? Of course, okay, that's no problem if the plastic doesn't have any metal in this composition. So that's the main idea. And also position antennas, so there's nothing between. It's what I used to say that if you with the transmitter, if you are the transmitter and you can see the antenna, the receiving antenna, you are okay. If you cannot see, the radio wave cannot travel easily. So that's the main idea. Keep line of sight is what we say. So think that the antenna should see the transmitter, and the transmitter should see the receiving antenna. And place the antenna close as possible to transmitters, so you don't have, like, for instance, long cables. Huh? If you use longer cables, you're gonna need amplifiers to compensate that loss, and you can use an active antenna to do that, and etc. But remember that a cable needs to be rated to be used for wireless systems. So use only 50 ohms cables, low less cables, and we're not going to cover cables and attenuation of cables here in this webinar. Take a look at the other materials that we have and manuals and etc. The first trick here, or the first hint here, is keep a distance from transmitter to the antenna, to the receiving antenna. Remember that the receiver has this RF meter, and it's going to show you how much energy it is receiving in that frequency. So if we put the transmitter too close to a receiver antenna, it will going to show, we're going to feel some RF distortion. So we don't want distortion. So keep the transmitter a little far, a little distance from the receiving antennas. As you can see here, as a rule of thumb, like 5 meters for active and directional antennas, and 3 meters for like omni dipole antennas. This is an idea, suggestion. Of course, that sometimes you need to use a little bit closer, but remember that the receiver is receiving that energy. If it receives more than it can work, you're gonna have some distortion. We're gonna present some RF distortion on the receiver. So it's very important to keep the distance. Also, the distance between in-ear monitor antennas and microphone antennas. Keep a separation also. That's very important. And it's very common to see both in the same rack and both with the antenna close to each other. That's really bad. Remember that this receiving antenna, the microphone antenna, is waiting for a very weak RF signal coming from your microphone. And you don't want to overload this antenna and input circuitry with the RF power of this very powerful in-ear monitor transmitter. As I said, keep antennas away from metals, from conductors. So this is very, very common structure in shows, in events, in any kind of situation. So keep the antenna apart from this. Of course, that if you have a directional antenna, you can put the antenna closer to the structure. Why? If you remember about the here rejection of the helical antenna that displayed it's a conductor, and etc. You're gonna remember that you can put the antenna closer to the metal, closer here to the structure. Of course, that an omni antenna, you can't. You need to put more distance between them because it's an omnidirectional antenna. So it receives energy or it sends energy in all directions. So keep that in mind. So I have some pictures. Of course, that there's 100 or more than 100 pictures available, but just some ideas and some practical usage, of course, to keep antennas in. No, there's no other structure here, metal structure here close to the LPD antenna, so it's very good. It's very easy to use. Here, you can use the structure, of course, that in this wall, it's a conductor structure, but of course, these two antennas are a directional antennas, so I can do that. I can put close to the structure. I have here another example, a very useful example of using a omnidirectional antenna in a very huge stage, in a very huge area. I used that antenna in a show to spread the in-ear for all over the place. So there is no other structure near to the antenna, and I take advantage of using an omnidirectional antenna to spread the energy to all the areas that I need. So now we're gonna show some bad ideas, some bad setups also. What we can do, what we can't, we don't want you guys to do that. Please don't put antennas close to each other. That kind of setup, it's bad. Now you can understand that this changes how the antenna receives the signal. You are changing the pattern of reception of these antennas. So you can have bad reception, with that kind of configuration. And don't put antennas inside racks, inside metal racks, close to metal surfaces like this. So it can work like for transmitter very close to the rack, they're gonna work, etc. Of course, but we're gonna have bad reception. We're gonna decrease the range of reception, etc. That kind of setup is what we call like the antenna farms, like two or three trees, one in the side of the other. So don't do that. That's bad. That's gonna change the reception. It's not the cleverest idea. Please keep that out of your mind. Use always distributors to distribute two antennas to all your receivers and etc. Here's the example of an in-ear monitor close to a mic antenna also. Don't do that. It's bad to the microphone, and also it's bad to the in-ear transmission. Keep antennas away from high-power RF sources like high-power radios, walkies, intercom systems, any other kind of high-power energy transmitters. And also keep antennas away from interferences like LED panels, like I said, wireless intercom, digital TV antennas, and any other wireless systems, transmitters, or receivers. So keep in mind that your antenna, it's your ears. If you want to listen to the speaker, you don't want two speakers speaking to you at the same time. You don't want a rock or a wall in front of your ear so you cannot hear the speaker. Keep that in mind. The antenna, it's a transducer. It used to receive or transmit a RF signal. So it needs to be apart. It needs to be separate from that structure to maximize its efficiency. Okay, so that's for now. I'm going to put here some online research that we have about this matter. Of course, that we have our wireless guide with antenna setups, diagrams, and photos. We have two wizards, like we say that, like two online tools. I didn't put here the shortcuts for that website, that links, but put wireless accessory wizard Shure at Google or any other search browser that you have with these two names, we're gonna access this page that can help you do decide the cables, the antenna types, the cable length, the distributors, and everything related to antennas for your setup or your project. Okay, here we go. That's the questions.
All right. We have a couple of questions, so let's dive in. First question. Is there any solution available where we can transfer signal wirelessly over a long distance around 1 kilometer? The use case is I have two mixer consoles 1 kilometer away, and I want to send signal from one mixer console to the other mixer console wirelessly.
Good question. Yes, there is some solutions on the market. You can do a little research on RF to optical or to fiber converters. There is like, I don't know, 3, 4, 5, or 10 different types or brands that do that kind of product. Take a look. Take care that uh, any conversion, if you want to convert a wireless, a coax, a RF signal to digital, like to be transmitted in a fiber, we're gonna have some conversion. So if the conversion is not good enough, you can add noise and distortion to your RF system. So take a look and try to find some brands that do that kind of converters, RF to fiber, and you can do that like for some 100 meters or kilometers and etc. But take care about the noise floor and the distortion that these units can add to your system.
Great. Okay, next question, just a clarifying question. Could you repeat how far from metal surfaces antennas should be?
Okay, depends on the frequency that we're gonna work. What I show here, what I shown here is it was related to the UHF band. So we suggest, for instance, like 1 meter for a omni antenna, and like depending on the kind of directional antenna, can be half meter or 0.2 meter or 0.1 meter,
Okay. Um,
for instance.
Great. Is it possible for the PA805 to both transmit and receive at the same time?
Not actually. Actually, let's explain that bit better. An antenna, if it's passive, it can transmit and receive at the same time. But if we want to connect a passive antenna to both a receiver and a transmitter, we're gonna need a special RF device that can separate both signals. It's like imagining that we're gonna have like a microphone that has his own speaker. So it's not very easy to do. It needs a specific and electronic for that. I'm not saying it doesn't exist. You can have, for instance, I don't know, a mobile that has only one antenna inside that transmits and receives two signals. It's possible, it's doable, but not for like our market, not for our kind of work that we do. Normally, we use separate antenna for transmitting and one a separate antenna, sorry, for receiving.
Okay. Is there a bypass switch for the active LPDA?
A bypass for the active LPDA.
Yes.
Actually, our LPDA UA874, it has the 0 dB, but it doesn't have a pass through. No, the question may be is that you want to use the active LPDA antenna as a in-ear monitor antenna. No, you cannot use. In 0 dB, the circuitry, the amplifier circuitry is still there. It's still working. So you cannot pass through easily. The 0 dB position is not a pass through.
Okay. Um, So the UA does the UA 864 have a variable polarization that is selectable on the circuitry?
The UA 874,
864.
no, 864, sorry.
That's right.
No, take a look at the manual, my friend, and it shows that it has the transmitting, the receiving elements or the antenna elements inside the box. They have some orientation. So if you take a look, the antenna in your front and the logo, the Shure logo is on the left bottom. The orientation is like, for instance, vertical. So this is the orientation. If you put that in the wall in that orientation, it's gonna be horizontal. Vertical. And if you put the logo in the vertical position, the orientation is gonna be horizontal. So whatever. Take a look at the manual. It explains very clearly how it's the suggestions of installation and how is the polarization depending in the installation. Okay.
Great. Okay, what kind of antennas are used in the BLX4?
BLX, it's a monopole antenna. The BLX uses a monopole antenna. It's the second antenna that we've shown here today. It doesn't mean that you cannot use other antennas. Uh, for instance, if you have a BLX, oh, sorry, it's a BLF4, not a BLF4R. Good question, my friend. Good question. I don't know exactly how is the antenna inside the BLX4. I suppose that it's oriented horizontally because of the size of the receiver. So probably is that. It's a very good question. I would try to find out more about that. But in the BLX4R that uses external antennas, of course, that you can use like a monopole antenna or whatever you want. But very good question about the BLX4. Maybe it's horizontal antennas inside the box.
Okay. Next question. You said keep antennas away from metal structures, but what about mounting them to a metal mic stand?
Good question. Yes. Yeah. Of course, that the mic tripod, it's behind the antenna, let's say that. It's away from the antenna elements. It's not on the side of the antenna, it's not on the front of the antenna, it's not on the back of the antenna. So a tripod is okay. Even when the engineers designed the antennas, they stood that. They understand that. They do tests in that situation because it's the most common situation that we're going to use antenna in a tripod, in a microphone tripod. So no problem at all. You can use the antennas in the tripod.
Great. Could you just repeat what the minimum distance between mic receiver antenna and IEM transmitter antenna should be?
Well, like we say like 3 meters, 2 meters, something like that. I usually to say that as far as you can put, it's gonna be better. So understand that um, it's the same idea of having a microphone in front of a speaker box. So if you don't want to have feedback, you want to put them apart. So how much apart? Well, it depends. If we're very close, half meter, we're gonna make a huge difference. If you are far, like 10 meters, from 10 meters to 12 meters, it's gonna make no difference. Huge difference. So that's the idea. That's why normally I say try to keep as much separate as you can, depending on the situation. I know that in real life we don't have the real situation. Normally, the architect or the stage designer or all the other stuff, the lighting, the equipment that you have in the stage, etc. You don't have a real situation. So try to keep them as far as apart. So I suggest normally 1 meter, 2 meter, 3 meters, if you can.
Great. Okay. Next question. Is it possible to combine two different antennas, for instance, an LPDA and a dipole, to receive on a diversity device?
Oh, yes, yes. You can use, for instance, one dipole antenna on the A input of your receiver, and you can use a LPDA on the B input of your receiver or your antenna distributor. There is no problem with that. Our professional wireless systems works very well if you use same antennas or different antennas. It depends on the scenario that you have, that the area that you need to cover and things like that. Sometimes I do use in the practical shows and events and big events, etc., different antennas in the diversity input of my receiver. No problem at all.
Okay. When choosing between VHF or UHF, what should be considered in your choice?
Whoa, that's a good question. It depends where you are. For instance, if you're not, if your country there is permission for first to use microphones in VHF, you can use. If the VHF range is clearer than the UHF, it can be good. So depending on all these situations, but just keep in mind that the antennas we're gonna be bigger. So the receiver antennas are gonna be bigger. The transmitter antennas are gonna be bigger. So if size matters here, you maybe have some problems. In a stage, sometimes of they cannot allow me to put the antenna in a corporate event, like a regular UHF. Imagine a VHF that is like four times the size. So keep that in mind. But it's a very useful frequency range. We have some equipment that works in that range, like ULXD, QLXD, Accent Digital, etc. So keep in mind that you can use that, but take care of all these points. Okay.
Great. Okay, next question. I use the Shure BLX with the Shure antenna power distribution system, so I'm going to assume that's a BLXR system they're using. When using quarter wavelength antennas, is 90 degrees the optimal angle between the antenna?
Yes, that's one very good idea and very good question. This is a very clever way to put the diversity to work better for you. As the antennas are 90 degrees apart, they were going to increase a little bit the reception or the efficiency of your diversity system. You can imagine that why can I do that with LPDAs? Why I don't see in shows the diversity antennas for the microphones, two LPDAs, one horizontal oriented, the other vertical, or both in 90 degrees apart. It's just a matter of, like say, maybe taste and common sense, because people feel that it's strange to see a LPD antenna like facing down or something like that, like in the horizontal orientation. But I saw a lot of some bands that do that regularly. So there is no problem using even with the LPDA with a 90 degree separation. It's just a matter how you install it, how it you can see it, how it shows, and etc. But this maybe it's a very good way to increase a little bit the efficiency of your diversity reception.
Great. Okay. Next question. What should be the minimum distance between LED panels and antennas?
Very good question also. Well, my friend, that's very tricky also, because it depends a lot in the kind and size of your LED panel. Um, I saw many LED panels that I could even put the antenna much closer than I would like to the panel, and it worked. Being very, very frank with you. So it depends in the kind of the panel. If the panel, the power supply or the electromagnetic shield of the panel itself, if they are not very good, it will gonna emit a lot of RF noise, and RF it will gonna probably cause any much more RF interference in your system. So it depends on the size also, because as you have much more panels, you're gonna radiate much more energy. So there is no rule here. Normally, if you have a receiving antenna in a receiving system, or a scanner, a AXT600, that you can scan your area, put the antenna in the position and do a scan, and ask the video guy to put an image and to put a video, even if you can, because it's better. The radiation that is transmitter, it's greater if you have motion, if you have video, than if you have the panel, like for instance, off or black. So sometimes there is one guy that asked me one question like this, like, Fernando, I did a coordination, the RF coordination during the setup, but the LED panels were off. Should I ask them to turn it on and put video? Yes, do that and do the scan again. We're gonna see a different animal, a different situation, a different spectrum. So there is no rule here. My suggestion is test it, scan it, and try to keep as far as you can to the LED panels.
Yes, indeed. All right. We've run a little bit longer than we normally do. So I just wanted, and we've got a lot of questions. So
Good.
unfortunately, I'm going to cut this off at 12:30, which is about 9 minutes from now. So I'm going to get through as many of these questions in the next 9 minutes as I can. However, we're not going to get to all of them. So I just wanted to make a note that if we don't get to your question, you can go to shure.com/contact and use that form there to open up a help ticket with our support team. We have a really vast group of really smart people that can answer a lot of questions across many audio topics. So if we don't get to your
Absolutely.
question, or if you have another audio question, go to shure.com/contact. And you can open up a ticket with those helpful folks. So, okay, we're going to get through as many of these we can now in the next couple of minutes. Next question. Does glass have any effect on antenna effectiveness? If my antenna are behind a booth window, will they still work?
Very good question. In my experience, I saw all kind of different glass. That's the problem. I saw some very thick glass without any problem, but there is some laminate glasses over there. So it's glasses with metal particles. So it's very difficult to predict. If you have any way to test, any way to measure, like you put the antenna before and after the glass or something like that, and test and prove it and see if it's something is changing, like the reception sensitivity or the range, or if you put the antenna, the hand, if you cover your transmitter antenna with the hand, it keeps cutting the signal or whatever, you have a problem. So it's very difficult to state if the glass it's good or bad to RF. Normally, what I saw, it's bad. It's normally the glasses, they have some particles or double glasses with laminate in the middle or something like that, and they were gonna block, or they're gonna attenuate a lot of RF energy. But better is to test, then you can see if it's gonna work or not.
Okay. Next question. Why do IEM systems use a single antenna while wireless microphones use two antennas?
Good question. Yes, because the IEM systems, they were gonna transmit one signal, and if I have two antennas, we're gonna transmit, like for instance, the same signal with two antennas. In my receiver, we're gonna receive two signals. That's maybe we're gonna be worse. It's gonna be bad because your receiver wants to receive only one signal, one frequency. If we receive two different signals with the same frequency, we're going to have like interference. So that's why basically in-ear monitors has only one antenna. Of course, that you can put two antennas in the IEM if one antenna is covering one area, if the other antenna is covering another completely different and apart and aside area. So if you, for instance, want to design a system for a TV studio that you want to put like the same IEM in two studios that are far apart, you can do like two antennas, a splitter connected to one transmitter, and it can work. But you need to have some measurements and to guarantee that you don't have leakage from one studio to the other. Because the receiver it's waiting very deeply just one signal, just one frequency. If it receives two, we're gonna have dropouts and noises and interference. So that's why the body pack, for instance, of the PSM 1000 has two antennas. It has two antennas of reception. So it will gonna have diversity reception in the body pack. It will gonna have more stable reception if we compare to a one antenna receiver, for instance. But the antenna transmitting, it's just one antenna.
Great. All right. Is there a distance limit when using a dipole half-wave antenna?
Sorry, is there any distance?
How far can you what's the distance when using a dipole antenna?
Ooh, yeah. So it's tricky. Normally we think about one wavelength. So if we have a UHF system that is coming from 470 to 600 or 700, think about more than half a meter or like 1 meter. So the safe distance is 1 meter or close to 1 meter. But you can ask me, but Fernando, if we took a receiver as you put here on one slide, the two antennas in the front of the receiver is like 45 or half a meter, 45 centimeters, one from each other. So that's enough. That's okay. If you're going to be a little bit bigger, you're going to be better. But half a meter, 1 meter is okay.
Okay. Can we use a 50 ohm antenna cable to extend the distance between two antennas in a receiver with a 1/4 inch antennas to get better reception?
Yes, antenna cables are made to be able to put the antenna closer to the transmitter or the receiver, depends if you are using the cable for IM or microphones. So yes, you can use a cable and put a dipole antenna closer to your microphones, for instance. The monopole antenna, as it needs a ground plane, the monopole you cannot use in a cable. The monopoles, they need to be in the chassis of the receiver or the rack or the distributor or whatever. So the monopole you cannot use with cable, let's say that. But the dipole you can use with cable.
Okay. Next question. Let's see. Actually, we're running out of time, so I'm gonna just actually skip to a question for myself. Can we get this presentation? As I mentioned at the top of the session, this webinar is being recorded. We will need a couple of days to a week to get it edited, but once it's ready, we will have it available for on-demand viewing at shure.com/webinars. That is shure.com/webinars. So this webinar will be there in about a week or so. And we have a lot of other great webinars from many, many years past across a lot of great audio topics. So please feel free to take some of your free time in the coming weeks and check those out and expand your learning. We want to thank you so much for joining us today. We are so sorry we did not get to all of your questions, but as I said, you can visit shure.com/contact to open up a support ticket with our support team, and they can answer any questions you have. Thank you so much for joining us. We hope you learned a little bit of something today. I know I sure did, and we'll hope to see you on the next one. Have a great day, everybody.
Thank you, everybody.